Okay, guys, lab this week upstairs. Any questions about lab? Okay, guys, let's finish up the elimination handout. Which one of these would eliminate fastest? What you need to consider here is the leaving group must be in which position to eliminate by E2? Yes, but which position does it need to be in this chair confirmation? Axial. Yes. We are doing an E2 elimination, right? Hydroxide. Okay. It actually could substitute. But I'm showing an elimination product. And it should be E2 because it's a strong base/nucleophile. Anticoplanar, but the iodine must be axial for that anticoplanar to be achieved. The question is really, which one of these is most likely for the iodine to be axial? And if you draw chair conformations and assess that, you will see that I think this one is going to be more likely for the iodine to be axial. Have we done chair conformations and looked at analyzing the two ring-flip versions? Yeah, we did that for test 1. So we do the same thing here, looking to answer which one of these would the iodine more likely be axial? Okay. Where did we leave off at? H. We're looking at some miscellaneous things as we finish up, both substitution and elimination. Deuterium isotope effect. A neat way to determine if an elimination reaction is E1 or E2. Look at the reaction. Alkyl bromide, that's called pyridine. It's nitrogen in a benzene ring. That's pyridine. Pyridine, we're doing elimination. Pyridine is taking the H. Okay, E1 or E2? Based on what you know already, E1 or E2?
E2.
Why E2?
Because sp3 nitrogen.
Nitrogen is not sp3. Hybridization of nitrogen is not sp3.
Because of heat. The added.
I can't hear you guys.
Because of the heat that's being added, then that makes a shift towards E2.
Make it shift towards what?
E2.
No, make it shift towards elimination, but not necessarily which mechanism. E1 or E2? How do you determine if it's E1 or E2? Bulky base. Bulky base distinguishes between Hoffman and Zaitsev products. Also, between substitution and elimination, the bulky base has nothing to do really with E1 versus E2.
Strong base.
Strong base would be which mechanism? E2. Weak base would be, so what do we need to do? We need to assess what? The base. Okay, is this mechanism E1 or E2? Is the base strong or weak?
Weak,
Why do you say weak?
because of the following ruling so far.
Which is what?
Ionic pair or sp2 nitrogen.
Or SP?
3.
Okay. Sometimes we said the sp2 nitrogen could be strong nucleophile, yeah? So this one's strong or weak?
Wouldn't those electrons be in a p orbital? It'd be right in those electrons.
For the nitrogen?
Yes, sir.
No.
Mhm.
No. Okay, final exam's coming up. Graph the hybridization of that nitrogen. Just like we did for test 1. What hybridization is the nitrogen? Hmm? What? Y'all want to talk like that? I mean, speak up.
SP2.
SP2, okay, let's graph it. Everybody agree it's like this? What type of bonds are the nitrogen making? Single bond to carbon, what else? Single bond to carbon, what else? Pi bond to carbon, what else is on the nitrogen? Lone pair. Nick, the lone pair is in what type of orbital?
S orbital. SP orbital, I'm sorry. SP2 orbital.
SP2, not a P.
Yes, sir.
Okay. Lone pair is not involved in conjugation or resonance. It's not in a P orbital, it's in a hybrid orbital. Okay. Can an SP2 lone pair be basic?
Yes. Yes.
The answer is it's borderline. Some people said we hadn't said that. You say yes. It's borderline. If it's borderline, is the mechanism E1 or E2? Hard to tell if the base is borderline. Would you like to know another way to tell?
Yes.
The deuterium isotope effect is a neat way to determine if the mechanism is E1 or E2. Okay, first off, before we do deuterium isotope effect, what way do you already know to tell if the mechanism is E1 or E2? Yes, you know rate experiments. How could you do a rate experiment to tell if it's E1 or E2? Double the amount of the base, and you would be looking for what?
See if the reaction rate doubles as well.
If it does double upon doubling the concentration of the base, what's your mechanism? E2. What if you double the amount of the base and it does not change the rate? It must be E1. Because we know that the base is involved in the rate determining step of an E2, but it's not in an E1. That's number one. Number two, deuterium isotope effect. Question, in which mechanism is the beta hydrogen abstracted in the rate determining step? In which of these two mechanisms is the beta hydrogen abstracted in the rate determining step? It's E2. What's the rate determining step of an E1? Leaving group leaving. Is abstraction of the beta hydrogen involved in leaving group leaving? No. But E2 is concerted. Base takes hydrogen, electrons in, leaving group off. All at the same time, that's your rate determining step. Base takes hydrogen. Okay? Well, that's important to know. Let's change the beta hydrogen to a deuterium, isotope of hydrogen. Now, what I have to tell you is a carbon deuterium bond is stronger than a carbon hydrogen bond. Slightly stronger. If the mechanism is E2, the reaction will then be more difficult. Because E2 would be these, it takes the D, these electrons move in here. But right here, the carbon deuterium bond is being broken. Right? It's gone. The CD bond is gone. But this is the rate determining step. If that bond's being broken in the rate determining step, by the way, that bond is also being broken in the rate determining step, then the reaction will be more difficult if there's a D there. Because that's a stronger bond. But if we put a D there and the rate doesn't change, that tells us that this bond is not broken in the rate determining step, which would be at E1, because E1 is not conserved. E1 is leaving group leaves, and we get carbocation, right? That's your rate determining step. This bond is not being broken there. At this point, then the base comes in, if we want to call it weak, then it comes in and you do this. But that's fast. That's the fast beta elimination, the second part of the E1. Breaking this bond in the fast step is not going to affect the rate. We're using deuterium. It's an isotope of hydrogen, and we're looking for an effect. That's why we call it a deuterium isotope effect. Make sense? It's based on the fact that a carbon deuterium bond is stronger. That only matters if that bond is broken in the rate determining step. I'm not sure the outcome of this. It's hard to determine because we don't know if this is a strong enough base to do E2 or not. You will see, well, isotope effects are sort of a common thing in organic chemistry. Bond strengths do change because it's a mass effect. The mass of deuterium, the mass of the atom can affect the bond strengths. You get into higher order chemistry, physical chemistry with a lot of mathematics. The mass of the atom can affect the bond strength. And you've got a huge difference here really because the mass of just regular proton is 1. The mass of deuterium, which has a neutron, as well as a proton, is 2. The mass is doubled. So that's why you see such a significant change in the bond strength. On the other hand, if you go from carbon 12 to carbon 13, the mass is not doubled. You have to go to carbon 24 for it to be doubled. And so when you get bigger atoms, changing through other isotopes is not as significant. But it's very significant here because you're doubling the atomic mass. Okay? All right, so that's the deuterium isotope effect. CD bond is stronger. It's going to be more difficult. Hey, here's one over here with a deuterium. Provide both substitution and elimination product for each of the following reactions. Okay, substitution product here. Somebody got it already? Hopefully you've already done these. Substitution product. Anybody got something?
Just get SMT, because it's a KOH.
Okay, and so what's your product?
Backside top from versions there.
Yep. Mm-hmm. SN2 it comes in inversion, right? Hydroxides the nucleophile. Kick off the leaving group with inversion. SN2. That's isopropanol. That's just what? The solvent. SN2. Okay, show the elimination product. What mechanism are we doing? E1 or E2? E2? Somebody got it?
We're going to put the bond between the BR and the material, replace this. Just have a double bond on the right side, right?
Is the deuterium still in the product or is it gone?
It's gone.
It's gone?
I mean, it's, the H of B is going to take.
Right there?
I have a question.
Huh?
So, why is the material in this product and not the last product? The one we did on the other page?
That's the removal.
Oh, right.
Cause what?
Never mind.
That's the removal of the hydrogen. And there's the deuterium is the rate.
Well, the previous one, you have to remove the deuterium to get the product I showed. This one we have a choice, and we have to make decisions. Okay? You got two beta carbons. You got hydrogens on both. Okay? Let's draw everything in. There's an H there. There's an H there. And there's an H here. Let's call that A, B, and C. And that's D. Okay? All right. What are our all possible theoretical elimination products? Of the four here, A, B, C, and D, there's only two that are going to be eliminated. What are the two?
B and D.
B and D, because they're the only two that can be anticoplanar to the bromine. Transcoplanar. They got to be trans to be anti. B or D. Removal of HB would give the product I showed. Removal of the deuterium would give double bond here, HC remaining. Well, if we don't draw in the H's, that's it. There's an H there and there's two H's there. And that's just cyclohexene. Double bond up there would give that. Okay, which one's more stable? Looking at the alkene, that's disubstituted. That's disubstituted. They're both disubstituted. So which one's going to be favored? Which one are you going to get? Here's the thing. When we say this is most stable, we're really not looking at that being most stable whenever we make those decisions. What we're looking at is the transition state leading to this. The transition state leading to the more stable product is going to be lower. If the product is not as stable, the transition state leading to it is going to be more difficult. We're really looking at transition states when we say, states of Hoffman. All right? This is E2. Which transition state is going to be easier? Well, the product has very identical stability in terms of alkene. But do we know anything else that's going to change the transition state energy?
Maybe that deuterium is twice as heavy as the HB.
And so that makes what?
Makes it hard for to remove.
Yes, that's what we just said in the previous example. Yes. This is more difficult to remove. We're doing an E2, right? Concerted. So if it has a choice, which one would it rather remove?
HB.
HB. And that's my product over there. I removed HB. HA remains in the product over there. So does HC, because we didn't do anything over there. Again, because both theoretical elimination products are both disubstituted. Now, if I gave you one where removing the more difficult led to the better product, that's like apples and oranges, and that'd be harder to assess. But in this example, they're both disubstituted alkenes. I mean, if this D wasn't here, would you put double bond down or up? You would do either, because it's the same. Well, with the D there, you no longer would do either. You would do up because it's easier. Transition state leading to it is easier. Okay, down below, substitution product. Substitution product. SN1 or SN2? You only know two substitution mechanisms. You'll learn more in organic 2. SN1. What's the nucleophile in this reaction? What's the nucleophile in this reaction? Ethanol. What's the purpose of the silver nitrate?
Make it weird or better.
Facilitate ionization. Right? Silver ions. Yeah, it's carbocation chemistry. Anybody got a product? Anybody got a problem? This ether? Did I get that product? What'd you get? No?
Substitution product.
What?
You talking about the substitution product?
Yeah, substitution product. Yeah? John? What do we get? That? Okay. Questions about this?
Yeah, I've got that product, but how does the H get taken?
From the oxygen?
Yeah.
Okay, well, just like we've always taken it. Mechanism. This ionizes off. I could show complexing with silver, okay? It facilitates the ionization. We could do this reaction without the silver nitrate, but we know silver facilitates ionization, okay? Leaving group has to leave. Ethanol is not going to do anything. Lazy, right? That leaves, we get carbocation here. What next? Ethanol attack here? It could.
It's resonance.
But anytime you can make a better cation, we want to do that. Can we rearrange to a better cation? Yeah. Got two H's here. We can do a hydride shift. Boom, 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 boom. Get cation here instead. Now there's only one H here. The other H is over here. Right? Now the nucleophile gets off the sofa and attacks the carbocation. It's not strong enough to kick this off backside concerted, but it will attack carbocation. This is not the rate determining step. The rate determining step was way back over here. Right? This is more of a fast step at this point. I'm just going to draw that phenol. Boom, 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 boom. And now we have bonded here the oxygen. It has an H, and it has an ethyl, and it has one lone pair left, and it's a positive charge. And the question was, how do we lose the H? Well, something has to take it. What can take it?
Chlorine.
If we didn't include the silver nitrate, yeah, the Cl minus is here. But with the silver, we're going to make silver chloride. This is going to precipitate. It's going to be gone out of the reaction equilibrium. Any other anion that could take the... How about the nitrate? NO3 minus. Like a lot of times we have HSO4 minus, you know, the anion of sulfuric acid. What about the anion of nitric acid? I'm not showing this full here, but this takes the H. These electrons stay behind. And so the full balance reaction would be that product plus nitric acid plus what? Silver bromide? Silver chloride? Yeah? Carbocation chemistry with rearrangement. Nucleophile attacks. Weak nucleophile attacks. But then you have to lose protons. By the way, when you get to organic 2 and you do carbonyl chemistry, keeping track of proton is a big thing. Dealing with the proton. But we've certainly seen it many times here. Okay, elimination product here. E1 or E2? It's E1. And it's the same mechanism. It's the same intermediate. Everything's the same. The only difference is from the carbocation, instead of something adding to the carbocation, we do a fast beta elimination. And like the nitrate anion, I wish this was drawn out because that's why you guys work like this. I've always did this with bisulfate. I'll do it with nitrate, but all right, otherwise we're going to have to take time to draw this out. These electrons, okay, take the H, these electrons move in. And that gives that elimination product. But this is the exact same mechanism we showed on the first page of this. You got the handout on the first page? You've got this mechanism there. We did the same thing. On the very first page, didn't we have a carbocation? And we did a fast beta elimination? Under the E1? The difference is on the first page, we were using T-butoxide, a strong base. And we said the mechanism is not E1 there because you have a strong base. It's going to do a concerted. Is that the right product over there? Is that the right stereochemistry for the product? What does your textbook say about the stereochemistry of E1?
So it's stable.
What?
No stable. No, it's no stable.
Is that what your textbook says? Because sometimes there's a little variation. How does your textbook discuss E1 elimination? Consistent with what I've been saying? Is my product the most stable elimination product you could show? I drew a trans. Should we draw a cis instead? That's a trans. Okay, double E2 elimination. You can do this. Two leaving groups. Take this vicinal dihalide, treat it with two equivalents of potassium terbutoxide, strong base. We can do a double E2 elimination. What HCl are we going to eliminate first? This chlorine or that one? In some cases it may be difficult to say. Do we have any rationale? If we remove this one, the H that's here is here, HA. So we can eliminate HA and the chlorine, put double bond here. But maybe we can also eliminate HB and this chlorine and put double bond in the same place. But if we do that, we'll be left with a chlorine here. We're going to do both of them. Which would you like to do first, though? Because down here, there's no choice. The H is here, the H is here. you eliminate one double bond here, and then you eliminate another bond here. But here, there's a choice. Which one would you propose eliminating first? Cameron? Do you have any argument in your toolbox to make here? Somebody?
What did you want to do the first one first because it one's the most stable? The most stable part is
No matter which one you remove, you're going to put double bond here, and it would be the same substitution. The difference is chlorine would be over here versus chlorine over there.
no HB. That's because terpene oxide is bulky.
HB what?
It'd be HB because terpene oxide is bulky and it's less sterically hindered at HB.
That's a very good argument. It's a very good argument. Does anybody have a different argument? I like your argument. Let's remove HB first because it is most accessible. This anion here, inserted all together now. Boom, boom. Yes, these would be anti. See, that's something though. We have stereochemistry here. These need to be anticoplanar. But if we did this, what are the choices? Double bond's going to be here, chlorine here, T-butyl here, and that's it, with HA remaining here. Okay, that. But that's cis. Or would it be trans? We'd have to look at this anticoplanar. The problem is, in my example, I'm not giving you any stereochemistry. Yes, that's chiral, but I'm not telling you if it's R or S. So we're not going to be able to do anything. You have to know if it's R or S. Or relative would be helpful, but there's no relative here because that's not chiral. All you got is R or S, and we're not being told. So this may be cis or trans, okay? You may have to determine this. But from here, can we eliminate again? There's H here and there's an H here. Okay, here's something we've never done. If we eliminate again, we have to come in here and take this H. These electrons move here and these get kicked off. What would that give? That's a second E2 elimination. Concerted, beta elimination, pi bond in, leaving group off, what does that give? We now have triple bond here, one H remaining, that H is the lone remaining H, it's there. Over here we have terbutyl, and that's linear, sp linear. Okay? We did an E2, and then we did another E2. Twice the fun. There's some decision on which to remove first. If we have removed HA first, the intermediate would have been T-butyl here and chlorine here. Because we would have removed H in this chlorine, double bond. That chlorine would have remained. But we chose to remove the other one because we had an argument for why this chlorine here. Again, down here, there's no choice because you're removing HBr the same exact way both times. Okay, there's some decisions to make here. Any questions about the final elimination? Anything that looks odd about it? What's the relationship between the H and the chlorine in my elimination? Trans or anti. Are they coplanar? Yeah, they're anti-coplanar. What if they were cis-coplanar? Could we do the second elimination?
Then you have to have it transferred.
Can you eliminate cis-coplanar?
You can, but it's more difficult.
Exactly, yes, you can. It's more difficult. And usually if we can do anti-coplanar, we always do that. If this was trans, I would switch these. Trans refers to the big groups. That'd be trans. That means the H would be here, and if you eliminate it, it would be syn-coplanar. Okay, anything odd about this though? There's one rule that this is broken that we've never done before in substitution elimination. What's being broken here?
We're eliminating group off the double bond.
Very good. The leaving group is not on a tetrahedral carbon. This is the first time we've ever done it. And at one time I said we never do it. Usually when we say things, we never do it until we say you can do it. All right, until we say that there's an exception. This is an exception. That's something you should recognize. The second halogen has to be eliminated from a non-tetrahedral carbon. That's also very difficult. That's why we don't do it. And I'll tell you how to do it so you don't get in trouble. Okay? Don't get on the roof. Why not? Not so much as it's going to get on the roof, because I know you're going to get up there and fall off. We tell you things to keep you out of trouble. But yes, this leaving group is leaving a non-tetrahedral carbon. That's why this is a more difficult reaction. You're doing this week in lab. But the reaction you're doing this week is the hottest you've heated a reaction all semester, and probably all in organic too. You'll never heat a reaction this hot. 125 degrees. Why so much heat to do this reaction? Because that second elimination is relatively difficult. One of the main reasons being because it's leaving a non-tetrahedral carbon. Okay. Geminal dihalide, twins, on the same carbon like twins, it's a little bit easier because you don't have to consider an intermediate. You just eliminate one. If you eliminate once, you're going to end up with a phenyl and a bromine and an ethyl. Although you don't have any regiochemistry, but you do have stereochemistry. Because this is E. It could also be Z. There's no stereochemistry here at all. Probably a 50-50 mix, but don't worry about that. But then when you eliminate again, well, this could make it even more difficult. If this is the intermediate, and then we eliminate again to get triple bond with phenyl and ethyl, so we eliminate this H and the Br and put pi bond in here again, that third pi bond. How easy do you think this elimination is going to be? There's two things that make it kind of difficult. One is the leaving group is not on a tetrahedral carbon. What's another reason that this elimination from this molecule would be a little bit difficult?
It's not anti-coplanar.
The H and the Br are not anti-coplanar. They are coplanar. This is all planar, but they're syn-coplanar. That would be that's going to get even more difficult to eliminate. And at some point you may question, is this reaction even going to happen? Well, it is known to occur, but it probably takes a lot of heat. Okay? Double E2 elimination. Any questions about that? Final exam review. Both of those starting materials can be made using chemistry we've looked at. Deuterium effect. Deuterium effect is used more and more in drug development, drug design. This compound here I think is an HIV drug. It's a little bit old now, the same ideas apply. This compound in the body is metabolized by oxygenation right here. This carbon, an OH is put here in the body by metabolism. Okay? So we go from CH to CO. The CH bond is broken in the body by metabolism. Instead of CH, it's now CO. That H is gone from the carbon. This bond is broken. Well, this is not wanted because when this happens, the drug is no longer active, I think in this case. There could be various scenarios why you don't want this. You don't want this to happen. How could you keep this from happening? Well, a lot of times chemists will put fluorine here because it's very small and it almost mimics hydrogen, although not exactly. And then that bond is much stronger and it's not typically broken. That blocks this metabolism. But what's another way to do it? As shown here, more and more chemists are putting, instead of H, put a deuterium here. This bond's going to be more difficult to break, right? Everybody agree? Thus, it's going to slow this down. With the deuterium there, the drug will last longer. And putting the deuterium there is not going to change much. You just got one extra neutron. And that usually doesn't change the drug property hardly at all. But it can affect that one little bond being broken because the CD bond is stronger. We can slow down the metabolism if we don't want it. That's an application of the deuterium isotope effect. Okay, one last thing. I think that's the end, but let me show you a little something. A little review. Here we go. You can find flow charts like this to help you assess this chemistry. Okay, this comes from Journal of Chemical Education. Determining which reaction is going to occur. Because that's what you have to do here. You have to assess the reaction. Substitution, elimination. First question. Is there a tetrahedrocarbon with a leaving group? Such as a halide or a tosylate? If there is, yes, then you can do any of these mechanisms. SN1, SN2, E1, E2. If there's not, game over. Can't do those mechanisms. Everybody agree you got to have a leaving group to do this chemistry? Well, that's the first question. Okay. Now that you have this, is there a beta hydrogen? Because if there is, you can still do all the mechanisms. But if not, guess what? You can't do an elimination reaction because an elimination reaction has to have a beta hydrogen. Okay? Is the beta hydrogen coplanar with the leaving group? Okay? Is there a very strong base? We're about out of time here. Structure of the substrate. Is the leaving group on a primary carbon? If it's on a primary carbon, it takes you to SN2. If it's on tertiary carbon, it takes you to SN1. What if the leaving group is on secondary? Both SN1 and SN2 are possible, right? We've said all this. What if both SN1 and E1 are possible? Well, it asks you about heat. What if you're heating? Yes. Heat favors which one? Heat elimination? Okay, it's all here. Would you like me to send you this by email?
Yes.
Okay. I would never give you this at the beginning because you would just try to memorize this. Look at it and confirm your knowledge. Have a good day, guys. See some of you in lab. Quiz on Monday.